Okay, so this time we will now test the difference between two means. So in this hypothesis testing, the population standard deviations are known. Okay, so the important points that we need to remember is that in this hypothesis testing, two populations are known, the mu sub 1 and mu sub 2. Okay, since sigmas are known for the two groups, we have sigma sub 1, sigma sub 2. Okay, again, take note that we are testing here two groups, means of two groups. Okay, so it is also expected that the two samples are also given, one from each population. Okay, then two sample means sigma, x bar sub 1 and x bar sub 2, and the sample sizes for each population, the n sub 1 and n sub 2. We are referring these populations to be the groups that we are trying to test the differences of its means. Then we compare the two population means. So our null hypothesis would be we test that the difference between the two population means is equal to delta. So in most cases, delta equals to 0, meaning your mu sub 1 is equal to mu sub 2. Okay, when you test their difference to be equal to 0. Against the alternative that it could be that the difference between your two population means is greater than the delta, or it could also be that less than delta, or it could also be not equal to delta. So in this case, if delta is 0 and this is your alternative, then we say that mu sub 1 is greater than mu sub 2. And if your hypothesis value of the mean is less than delta, so we say that mu sub 1 is less than mu sub 2 when we set delta to be equal to 0. And we say that mu sub 1 is not equal to mu sub 2 when delta is set to 0. Okay? So this is a two-sided alternatives, or the one that we call a two-tailed test. So for the purpose of our discussion, we will set our delta to be equal to 0. So we say that the difference between mu sub 1 and mu sub 2 equals to 0 against the alternative that it is not equal to 0. So we reject the null hypothesis if the difference of the two sample means is too far from 0 in either direction. Okay, so the question is, how far from 0 might x bar sub 1 minus x bar sub 2 be if mu sub 1 minus mu sub 2 equals to 0? So the sampling distribution of the difference between the two sample means is asymptotically normal with mean 0 and standard deviation of sigma sub x bar sub 1 minus x bar sub 2. So we have to determine or to know the values of sigma sub x bar sub 1 minus x bar sub 2. If the sample means are from independent samples, then the population variance of your sampling distribution is simply the sum of the individual population variance of the sampling distribution. Okay? And its standard deviation is simply the square root of their population variances. Okay? And this one, that is equivalent to this, which is sigma squared sub 1 all over n sub 1. So this is basically the population variance of the first group, and this is its sample size. This one, that refers to this, the population variance of the sampling distribution. Okay, this sigma squared sub 2 is the population variance of your second group and its sample size. Okay, SE is the standard error. So this is the standard error of the first group, and this is the standard error of the second group. So this is SE squared sub 2. This is 2. Okay, thus, under certain assumptions, the Z-test becomes the difference of the sampling distributions minus 0, because we set delta to be equal to 0, divided by the square root of, take note that this is our, okay, that is our standard deviation. Okay, that's 1. So look at this one. You can solve it given the values of your sigma squared sub 1 and sigma squared sub 2. Take note that the variances are known because this is the test where sigma or the population standard deviations are known. Okay, so using a confidence interval, if the hypothesis value of your mean is within the interval, then we fail to reject the null hypothesis because it falls within the non-rejection region. Okay, so our hypothesis value of the mean is basically the value of delta. So in this case, we set delta to be equal to 0. Okay, if 0 is within the confidence interval, then we fail to reject the null hypothesis. Okay, meaning the two population means are equal. Okay, so differences between means, a two-sided alternative. Okay, so these are the assumptions. The population standard deviations are known. The normal populations, or it follows a normal populations, or the sample sizes are large. When do we say that the sample size is large? When it is greater than or equal to 30. Okay, so under the null hypothesis, we test the Z. Okay, so using the formula, and we normally use delta to be equal to 0. Okay, thus we assume that the two groups are equal in terms of its means. Okay, so this will be the rejection region. We reject the null hypothesis Z when it is greater than Z alpha when the alternative is this. The difference between the two population means is greater than delta. Then we reject the null hypothesis when Z is less than the negative Z alpha when the difference between the two population means is less than the delta, the value of your delta. Okay, then if it is a two-tailed test, alpha is divided into 2, then we reject either using the positive value of your Z or using the negative value of your Z. Okay, we use these rejection regions whenever we have a two-tailed test. Okay, example, two labs measure the specific gravity of metal. On average, do the two labs give the same answer? So mu sub 1 is said to be the population mean by laboratory 1. Then mu sub 2 is said to be the population mean by laboratory 2. Okay, so our hypothesis value of the mean would be, we test that mu sub 1 is equal to mu sub 2. Okay, data is all about the specific gravity of a metal against our alternative that the two population means are not equal. Okay, so the assumed mean here is that we test that the specific gravity in laboratory 1 is equal to the specific gravity in the laboratory 2 against the alternative that they do not have the same specific gravity. Okay, so the population variances or the population standard deviation are given. For laboratory 1, the variation is equal to 0.02. For laboratory 2, the variation is 0.03 or the population standard deviation. The sample size for laboratory 1 is 20 and for laboratory 2 is 25. And the sample mean in laboratory 1 is 2.032 and the sample mean in laboratory 2 is 2.020. Okay, since the population standard deviations are known, then we use the Z-test. Okay, So this is the confidence interval of a z-test. So here we get the difference between the sample means. This is z alpha. We already know how to determine z alpha using a z table. And this is basically the estimation of your variation. Okay, the variances are given in the problem. The sample sizes are also given. So you simply substitute them in the formula. Use your calculator. Okay. So first solve the values inside the radical sign. You multiply it with 1.96. Okay. So this one, the standard errors, take note that this is our standard error, is equal to 0.0075. Multiply it with 1.96. So we get this one. So first, to get negative 0.014, you simply use the minus sign or the difference. Okay, to get the 0.016, you use the sum or the plus. Okay, so take note that our hypothesis value of the mean is that we wanted to determine whether we can reject that mu sub 1 is equal to mu sub 2. So meaning delta is 0 when we test the equality of the population means. So if it is 0, okay, we cannot reject the null hypothesis when 0 is within the interval. So take note, this is negative value, this is positive value. Basically 0 is within the limits. So if it is within the interval, then we say that we cannot reject the null hypothesis. So we might conclude that there is insufficient evidence to conclude that the two means are not equal. Okay? So this is the other way of calculating the z value. So you simply get the difference. Okay, we do not have here minus delta because delta is already 0 or it is already set to 0. Okay, take note that the difference between the sample means is 0.012. It is also here 0.012. This is the sample mean of the first group or the values in the laboratory 1. This is the sample mean in the laboratory 2. Okay, and their difference is 0.012. That is why we have it here. This one, that is our standard error, this one. Okay, so that's 0.0075. Okay, so we get 1.6. Take note that we reject if it is greater than the z alpha. Our z alpha is 1.96. 1.6 is less than 1.96, so therefore, we fail to reject the null hypothesis. Okay, so for large samples, but the population variances are not known or the sigmas are not known, we still use the z-test because samples are large. The more we increase the sample sizes, it basically estimates the population. Okay, so we have here assumptions. When the sample size are really small, we assume population standard deviations to be equal, and we also assume population standard deviations to be not equal. Okay, so for large samples where n sub 1 and n sub 2 are greater than 30 or equal to 30, we use z. But instead of sigma here, we use s because sigmas are not known. So we estimate sigmas by our standard deviations, sample standard deviations. Okay, so here, since we set delta to be 0, we may or may not write delta anymore. Okay, so this is a t-test where sample sizes are small, but we assume sample standard deviation to be equal. Okay, S sub B is the pooled standard deviation. How do we solve pooled standard deviation? Okay, we use this one. Take note, n sub 1, n sub 2, they are known in the problem. S sub 1 squared and S sub 2 squared are also known in the problem. Okay, so to solve this, S sub b is the pooled standard deviation, S sub b squared is the pooled variance. Okay, so the pooled standard deviation is just the square root of your pooled variance. Okay, example, we compare blood pressures. Okay, so two populations given common variance. Okay, so here our sample sizes are really small, 10 and 12. These are less than 30, but we assume variances to be equal. So that's why we have here common variance. We set alpha to be 0.05. So we will solve first the pooled variance. Take note, this is n sub 1 minus 1. Then the sample variance of group 1. Then sample variance of group 2. Okay? So we have here 10 minus 1. And 16.2 is S sub 1. So we will square it to make it variance. And then n sub 2 is 12 minus 1. Then its standard deviation is 14.3. So square it to get the variance. And this is n sub 1, n sub 2 minus 2. So use your calculator to solve. You will get 230.6. Okay, S sub b is just the square root of 230.6. Okay, so when you get the square root of 230.6, you will get 15.2. Okay, the DF for this test is n sub 1 plus n sub 2 minus 2. Okay, because we already test two means here. In the previous lesson, we test a single mean. That is why DF is only n minus 1. But since it already involves two groups, our DF is n sub 1 plus n sub 2 minus 2. Okay, so the critical value, since it is a two-tailed test, okay, here our test is a two-tailed test. So we have here 0.025 because alpha is set to 0.05 divided by 2. We'll get 0.025. Let's try to look at this critical value in the t-table. Okay, t-table. So this is our t-table. We look into 0.025. This is 0.025. And the DF is 20. Okay, so this is 20. Then we have 0.025. So we have 2.086. 2.086. So that is why you have 2.086. Then solve your t. Take note, this is x bar sub 1 and this is x bar sub 2. Try to recall our given. So we have here x bar sub 1, x bar sub 2. So 125 minus 137. Okay, our standard error. This is the pooled standard deviation. Is 1 over n sub 1. This is 1 over n sub 2. Okay, so use your calculator to solve. You will get negative 1.84. So since this is a two-tailed test, we can get the absolute value of t and compare it with the t tabulated. So the t calculated is negative 1.84 and the absolute value of it is positive 1.84. Take note, it is not greater than the t tabulated. So therefore, we cannot reject the null hypothesis. You can also check that one using the confidence interval. You try it on your own. Okay, using the confidence interval, the lower limit is negative 1.6 and the upper limit is 25.6. Basically, 0 is within the interval. Therefore, the delta, the value of the delta is within the non-rejection region. So we fail to reject the null hypothesis. Okay, for another test where we assume an equality of the population variances, or the population standard deviation. The test is still t. However, we do not use the pooled standard deviation. Rather, we use this standard error. Okay? So this is our t-test. Earlier, we used the pooled standard deviation, but inside the radical sum is 1 over n sub 1 and 1 over n sub 2. Okay? Be familiarized with the test. So if we assume equal variances or equal population variances, then we use the pooled standard deviation. But if we assume unequal population variances, we use this t-test. Okay, but this is the DF. So DF is quite complicated for this test. Okay. So let's say, for example, this is so the only difference when you assume equality of population variances, you use the pooled standard deviation. But if you assume unequal population variances, you use this formula for the t-test. So this time, we will discuss paired data sets. Let's take this example. 1982 study of trace metals in South Indian River. Okay, there are 6 random locations. We have first location, second, third, fourth, fifth, and sixth. Okay, T refers to the top water zinc concentration. B refers to the bottom water zinc concentration. So for this location, the researcher determines the zinc concentration on top of the river and zinc concentration at the bottom of the river. Okay, so we have here first sample, second, third, fourth, fifth, and sixth sample. So in all, we have 6 sample locations. And the data is all about the zinc concentration of the river. Okay, so what makes it paired? Because for every location, the water zinc concentration is determined. So we try to test whether the zinc concentration on top of the river is the same with the zinc concentration at the bottom of the river. Okay, so let's for example, we have this data sets. We have this data, the water zinc concentration on top of the river and the water zinc concentration at the bottom of the river. Here D refers to the difference. D refers to the difference between the top zinc concentration and the bottom zinc concentration. Okay, so these are the differences. So our hypothesis value of the mean is, we say that the difference between the water zinc concentration on top of the river and at the bottom of the river is 0, meaning the water zinc concentration on top is equal to the water zinc concentration at the bottom, against the alternative that it is greater than 0. So since this is B minus T, mu sub D here refers to the water zinc concentration at the bottom of the river is greater than the water zinc concentration on top of the river. So that's what the alternative tells us. Okay, so trying to solve the T calculated, D bar is the mean of the differences. So just get the mean of these differences. That is your D bar. And you can solve that one on your own. You will get 0.092. Okay, this is standard deviation, or the S sub D. If you could still recall your formula of your standard deviation, it's basically the square root of Okay, so take note, this is our formula for our standard deviation. So instead of the variable x, since we are after with the differences, then we write it here, n, the sum of d squared. Okay, our d refers to our differences. Okay, these are the values of our d. Okay, then we have it here, the sum of d raised to 2. Okay, our n are the locations. N is just equal to 6 because we have 6 locations in our problem. Okay, use this formula to calculate for your S sub d. Okay, sigma sub d bar is just equal to S sub d divided by the square root of 6. And you will get 0.025. So with the help of your calculator, your t calculated will be 3.68. Okay? So in the example, we set alpha to be 0.05. And take note that our alternative is a one-tailed test. So we will not divide alpha into 2. Our df is simply n minus 1. Okay? So our n, there are 6 locations, n is 6. Okay, minus 1, so we have 5. We will look at the t table. Okay? So our n is 0.05. I mean, our alpha is 0.05. And our df is 5. So we get 2.015. Let's see. 2.015. Okay. The t calculated 3.68 is greater than 2.015. Therefore, we reject the null hypothesis. Okay? So we conclude that there is sufficient evidence to conclude that the means or the differences of the means between the bottom and the top. Okay? Let us recall the problem. So this is the problem. So since we reject the null hypothesis, and our null hypothesis is that the zinc concentration between the top and the bottom of the river are equal, and we reject that null hypothesis. So we conclude that the water zinc concentration at the bottom of the river is greater than the water zinc concentration on top of the river. Okay, that's how you conclude your decision since we reject the null hypothesis. Okay, so I will be posting some word problems which applies the Ztest and the Ttests. You could also look for word problems in the book that I gave you, or in some statistics book, and then apply the things that we have discussed.